Okay, in this hour, we're going to introduce a new neural network layer, which is called convolution layer. And let's take a look at this figure. It is a very typical dense neural network. We talk about dense layer last week. Okay, we have m different features from the left-hand side, and since we don't know what is the exact relationship between x and the output y, so we can design several hidden layers, and for each hidden layer we can design several different hidden neurons, and we use a fully connected graph to connect all the neurons from the input layer, which is the big X right here, and the hidden layer, which is the big H right here. And as you can see that the information will be passed through the network from the left-hand side to the right-hand side to Y. And we can see that Y can be a single value. And you can use this single value to perform, for example, the regression. And or it can be multiple neurons at the output layer. As you can see that in this example, we have 10 different neurons at the output layer. Okay, and it's it is very useful for application that for classification, to classify, for example, some data point to 10 different classes. Okay, so that is a very general form of a dense network. Okay, and we mentioned before, for each neuron, usually we have the red circle right here, and it is the activation function. Okay, it is the activation function to simulate the nonlinear relationship between the left-hand side and right-hand side. Okay, so and of course, at the output layer, usually we don't at the output layer, usually we don't add activation function on the output layer if it is a classification problem. So usually we put a spatial, we can say that activation function at the output layer of the classification problem, which is called softmax. Okay, because Y, for example, it is a classification of 10 different classes, and of course there are 10 different values at the output layer. So usually we will choose the biggest one neuron, the neuron with the biggest value to assign its output. Okay, we only choose the biggest one. But sometimes the value is a little unpredictable, so sometimes we use another activation function designed specifically for the output layer, which is called softmax, and that is the definition of softmax. Okay, so if we have 10 different output values, y0 to y9, and its output value, okay, should be further processed, okay, like this one. Okay, for the output of y0 neuron, okay, and the additional process is that we get the sum of the all outputs and put it right here, and y0 is divided by this value. So we can see that this is some kind of normalized the output. Okay, so all the output will be in the range of 0 and 1, and it somehow feels like a probability. So it is the meaning of the output of y0 prime means what is the probability of the input value falls into class y0. Okay, so in addition, for the classification problem, okay, we will further add additional softmax post process on your neural network. Okay, but that is the dense network, right? So this week we will talk about convolution. So basically, dense network receive all the information from the previous layer, right, and process it and pass it to the next layer. But human beings are very smart. Sometimes we notice that it is not necessary for a neuron right here to receive all of the information from x1 to xm. Okay, and here is an example. Okay, we will show the example is MNIST dataset. Okay, it is an image dataset. Okay, in total it has 70,000 images. Okay, the images look like this. Okay, you can see that is handwriting of numbers, right? So we have 10 different classes, 0, 1, 2, 3, 4, 5 to 9, right? So for such kind of data, okay, it is an image. Okay, so we in the training data set we have 60,000 images, and for the testing data set, okay, we have 10,000 images. And of course, we have the corresponding labels. Okay, it is either 0, 1, 2, 3 to 9. Okay, and the images, okay, itself. Okay, let's take a look at this one. Okay, apparently it is a 9, right? But the data is represented as pixel. So basically, it is a 28 by 28 pixels, and for each pixel, okay, it is an 8-bit representation of the color. Okay, it is a grayscale picture, right? It is grayscale picture. So for 8-bit pixel, okay, the range is from 0 to 255, and it indicates that the 0 means black, and 255 indicates white. And for all the other numbers between 0 and 255, they are gray color. Okay, so you can see that there's some different gray colors right here. So in order to represent this picture, this image of handwriting numbers, okay, you can simply just use, it's right here. You can simply just use a matrix, okay, and it is a 28 by 28 matrix. Okay, each number right here represents a pixel. And as we mentioned, the color is either gray or black or white. Okay, the number should be between 0 to 255. But before we process this data, okay, we use it's right here. We divide the integer by 255 so that the number will become from 0.0 to 1.0, something like that. So let's take a look at this one. So 0 means there is a black dot pixel, okay, black, and so on and so forth. And for some numbers right here that indicate that it is a gray color, okay, and it's 0.65. And for some numbers right here like 0.99, that is a white color. So this is a grayscale image, 28 by 28, and all the numbers in this matrix, they are real numbers between 0 and 1.0, indicating it is either black or white or some gray color between black and white. Okay, so that is the input data we have. We want to use this input data and its corresponding y, which is the actual category number, okay, actual category. So basically, of course, we can use a dense neural network like this one, okay. So we have 28. So the m number right here is 28 times 28. We have 764, I think, pixel, and all of them are numeric numbers. Okay, so we can design a very big neural network which input size is 28 by 28, and we have several different neurons, several different hidden layers, and come up 10 different categories. It is doable, But some smart people believe that if we can do some special design, and it will be more efficient to analyze such kind of two-dimensional data. Okay, the idea is that it's right here. The idea is that if the image looks like this one, okay, so we have several different pixels. For example, 20 pixels right here. Okay, if we have 20 pixels, and of course, you can use a table to represent the image. Okay, we have x1, x2 to x20, right? And we can put in the numbers. Okay, the color right here, the grayscale color right here, something like that, and to do prediction. It is doable, but think about one thing. When we talk about the dense neural network right here, okay, for example, right here, it is really doesn't matter if you put the first pixel on neural x1 or you put the first pixel right here. For dense neural network, it really doesn't matter because all the features are independent. Okay, but take a look at this figure. It is an image, right? It is an image. We have 20 pixels right here, and you can see that for some pixel right here, this pixel, that is x15, and because we are human beings, I say human beings are smart, and we can see that for this specific pixel x15, there are several different, there's some pixels around it, surrounded by this specific pixel. Okay, that's x10, 11, 12, 14, 16, 18, 19, 20. So we believe such kind of information should be valuable. So we should design some structure to preserve such kind of information, which means x15 is surrounded by 10, 11, 12, and 20. So in this case, we can somehow design a new layers to preserve such kind of information. Okay, so that is the idea of convolution. So I would like to maybe we can draw it again. Okay. So I will draw a figure again at the right hand side, but it should look like the left hand side. Okay. So again, we have several different pixels. Something like that, okay? So at first place, when we analyze is the neuron, okay? That is x1, x2. When we design when we design the neural network, we have the first hidden layer and the first neuron, which is H1. And in dense layer, H1 will receive all the information from x1 to x20, right? And for H links, okay, there should be a weight right here. The weight indicate how important the neuron in the previous layer, right? Because the weight, if the weight is large, that means the x1 is important than the others. If the weight okay, we write it in this way. If the weight W21 is smaller, that means X2 might be less important than X1, and so on and so forth. And we accept all the neurons from the previous layer if you use dense network. But for convolution, okay, there's another thought. Another key concept is called kernel. kernel. Okay, kernel has a size. Okay, let's assume the size is 2 by 2. So you draw a 2 by 2 kernel right here. That means when we design H1, okay, which is the hidden neuron, okay, we don't accept all the information from the previous layer. We only accept a small part of the information from the previous layer. And the kernel size is the focus group. Okay, so in this group, there are only x1, x2, and x5, and x6. That is because in this image, these 4 pixels are close enough. They're together, right? So for H1 neuron, it only focuses on these 4 specific inputs. And of course, there should be some weights right here. Okay, there should be some weights right here. The green weight. And again, for the next neuron, okay? And it focuses on different groups, okay? So you can simply just move your neuron on your original image. So we move it to here. And to move this, we call this stride. Okay, a stride. Okay, so the stride, okay, makes the next neuron, hidden neuron at H2, focus on X2, X3, X6, and X7. And again, there should be a weight on the links between X2, 3, 5, 6, and the H2. So every time you can create a new hidden neuron, and it depends on your kernel and your stride. Okay, so the next one will be 3, 4, 7, and 8. And there should be another weights right here, the purple weight. And at the end, you move your kernel to the next row. And as a designer, you can design how your kernel moves. So if I write stride 1, 1 right here, means every time I move to the right column, okay, by one column. And at the end, the next one, let's say, if you move to the end of the rows, okay, and then you move down, okay, so the next kernel will be right here, x5, x6, x9, and x10. So the one right here means you move to the right 1 column at a time, and the one right here means if you at the end of the image and you move down 1 row at a time, and so on and so forth and so forth. So that is the definition of stride. Okay, and of course you can design you can configure your kernel to whatever shape you like. In this example, it is 2 by 2. It can be 3 by 3 or 1 by 3, 3 by 1, 2 by 3. It's really depend on how you think you should move your kernel and what is the size of your kernel. In this case, those neurons H1, H2, and H3, they only focus on a small group, and those group, because they are neighbors, right? X1, 2, 5, 6, they're neighbors. So we only focus on a local information to see if H1 should activate or not. And of course, you should add some non-linear activation function on your hidden layer. Right? And next thing is that if you move like this way and to the the end of this image. Okay. Okay. The last kernel will be x15, 16, 19, and 20, right? But think about one thing. If you do so, the last hidden neuron will be H12. Okay, originally you have 20 pixels, but since your kernel is 2 by 2 and your stride is 1 and 1, and at the end, the final the last hidden neuron will be H12. Okay, so the size, okay, the size from big X, okay, from big X to big H decrease. Okay, sometimes mathematicians don't like to shrink the size, so most of the time when we do such kind of calculation, we will add additional padding we'll add additional paddings right here. So in this case, okay, when we move our when you move the kernel, okay, there will be additional kernel right here as H4, right? H4 as H4 right here. So in this case, the last hidden neuron will be H20 as well, because we have additional paddings. So in this case, the size of big X and the size of big H is the same. Okay, because it is more convenient for us to do some to calculate to design the size of the network. Okay, so that is the idea of convolution, and after that, okay, as we mentioned in the dense neural network, you can see that there are lots of weights right here, right? We have several different weights. So if we have 20 different hidden neuron right here, then we will have 20 different sets of weights, and for each one it has 4 different weights, right? Because we have the kernel size is 2 by 2, right? So ideally, H1 would be something like this one. Okay, for example, if the green edge looks like this one, green like this, so H1 will be an activation function, right? And there will be W1, W2, W3, W4, and there will be X1, X2, X5, and X6. Okay, that is how you calculate H1, and so on and so forth. You have several different weights on on the other hidden neurons. But okay, there's an important thing is that in convolutional layer, okay, we manually set, okay, those weights, the green one, the green one, the blue one, the purple one, the yellow one, all the weights to be the same weight. That means, okay, that means H2, okay, it has only they still use W1, W2, W3, and W4 to calculate. Okay, H2 would be X3, x4, sorry, x3, x2, sorry, it will be x2, x3, x6, and x7, and so on and so forth, until h20. We manually decide that all the weights on this kernel will be this one, okay? And this kernel, they use the same weights, okay? I will tell you why, okay? And so in this case, we have only 4 weights, W1, W2, W3, and W4, to describe how H1, H2, and H3, and H20 are populated, right? Because right now we don't have so many colors on weight, okay? Those green, blue weights, those weights, they are all the same. They're the same weight. Okay, and so we have only 4 different weights to describe the information between big X and H, and it is not that useful. So we write it right here. So we say that it's K equals 1. The K means kernel. So that is the first kernel. For the first kernel, okay, we have same weights, W1, W2, W3, and W4, the green one. And we use it to go over all the entire images from X1 to X20 and plus the paddings, okay? So we can generate H1, H2 to H20, okay? But they use the same weight. That is K equals 1. And again, okay, and again, we can use we can set K equals 2, right? And right now we have another weights right here, and we have another H1, H2 to H20. And for the second kernel, okay, we have another weight, and those weights, of course, are shared in the K equals 2, right? And so on and so forth, so on and so forth. So in this case, we will use several different kernels, and those kernels are different kernels. Okay. For example, if we have 32 different kernels, so we have 32 different set of kernels, and each kernel has different weights, and those weights, 32 different weights, will go through the entire images, and it will calculate the corresponding hidden neurons in this way to generate 20 different neurons for each kernel. So if we have 32 different kernels, and then we will have total kernels, and for each kernel we have additional 20 hidden neurons. Yeah, so in total we will have that much neurons at this second convolution layer. So that's how we described the how we pass the information from the X to the big H hidden layer, convolution layer. Okay, the reason why we use a shared weight is something like this one. Okay, we'll take a look at this one. Okay, so for certain neuron, okay, the definition is right here, right? So basically it is a matrix, okay, that another matrix. Okay, so think about the definition of an image, okay, x1, x2, x5, and x6. It is a small pieces of pixel. Okay, so basically, if x1 is 0, x5 is 0, x2 is 1, and x6 is 1. Okay, so that means okay, 0 means black, right? 1 means white, black. That is a small pieces of image, right? It has 4 pixels, 2 by 2, and the pattern is like this one. Okay, and think about the weight, for example, right here. If the weight, okay, although we say that the weight initially they are randomly weights, right? We need to perform gradient descent to get the optimized weight, right? But at the beginning, it is a random weight, okay? We don't know how, actually, after gradient descent, okay, there will be a W star right here. So let's assume the W star looks like this, okay? So take a look at this one, okay? We have a green weight, which is 0, 1, 0, 1. And the X, the image, is still is the same, 0, 1, 0, 1. So if we product these two matrices, the number will, the final answer will be 2, right? 0 times 0, 1 times 1, 0 times 0, 1 times 1, and sum up them together. So that result will be 2. That is a very large number, right? And after that, we put it into activation function, and we know activation function, okay, they are increasing function. They're increasing function. So there will still be a large number after after activation function, right? So if the number right here, is large, that means this neuron will be activated. So the information will be passed to the next layer. So if this number is small, then maybe the activation is small or even negative, okay? For some activation function, the output number might be 0 or negative number. So that means this neuron is not activated. So that indicates if the number is 0, okay, that means we don't pass any information from this neuron to the next layer, right? So if this information, I mean x1, x2, x5, and x6, they are very important, and that means we should pass such kind of information to the next layer. So the corresponding weights right here, W1, W2, W3, and W4, should be very similar to x1, x2, x5, and x6, because if we times them together, the result will be large. And after activation function, the number will be large, not 0. So that means, although at the first beginning, the weights, okay, if we have several different kernel, okay, that is the first kernel, that's the second kernel, that's the third kernel. Although at the first place, the kernel is randomly populated, but after gradient descent, there are W star, okay, W star, W2 star, W3 star. We have several different kernels. They are optimized, and those kernels, they are trying to seek or trying to find, okay, some important patterns in the original input, right? If x1, 2, 5, 6 is very important, and they are similar to certain kernel, the sum product will be large. That means it's important information, so it should be passed to the next layer. If some pattern x1, x2, x5, and x6, they are not important, they are not similar to this kernel, or this kernel, or this kernel, if they are not similar to any of the kernel, optimized kernel, that means x1, 2, 5, 6 is an unimportant information. And after activate, if you choose ReLU, the number should be 0. That means I don't want to process this data in the next layer. So that is the concept of convolution. Although we don't know what kind of pattern we are looking for, but under this design, after we have n different input data, after gradient descent, we will have an optimized kernel, several optimized kernel, and it indicate what kind of information should be identified in the original images. So that is the concept of convolution. Okay, take some time to think about it. Okay. So let's take a look at the code right here. We will talk about this figure later. Okay, so again, we have a sequential model because the information is processed from the left hand side to the right hand side, so it is still an sequential model. Okay, we have 4 different layers right here. Okay, you can use model add to add layer. Okay, or you can use a model and use a list to list all the layers in a Python list. But you can use add to add the list. No matter you use add or use a list, they're the same. Okay, so we use add in this example. Okay, first we add a convolution layer. The 2D right here stands for 2 dimension. So it means we can design a 1D convolution. So let's take a look at this one. Okay, if we have some data which we believe the relationship between different features, they are related according to their position. For example, in this example, maybe x2 is highly related to x1 and x3, and you cannot exchange them. So it is not that suitable to use dense neural network, because as I mentioned, dense neural network does not consider the position of the data. Okay, so if you have a one-dimensional data x1 to x5, and you can use 1D convolution, you can design a kernel with size of 3, x1, x2, and x3. So the graph would be something like this one. There you have a hidden neuron, and you simply just take a look at the x1 and 2 and 3. For the second neuron, you take a look at 2, 3, and 4, and so on and so forth. So you don't use a dense network. You can simply just use one dimension convolution layer. Okay, so only part of the links will be connected from the input layer to the hidden neuron. Okay, so here we have a 2D convolution because we have an image. Okay, the image is 28 by 28. So first, we set the filters. The filters right here, it means kernel. The kernel, I want to have 32 different kernels, and each kernel, its size is 3 by 3. Okay, 3 by 3. And the stride is 1, 1. We explained it before. And the padding is same. The same means, yes, I would like to have padding, so that the size of the X and the size of the hidden neuron will be the same. So that is same. Okay, and we have a activation function, which is where loop right here, and the input size is right here, and name I have a name, first convolution 2D. Okay, so this configuration specifies how we connect the neurons in the convolution layer and neurons in input layers. Okay, so that is the first layer. Okay, the second layer is a little bit different. It's right here. That is called max pooling 2 dimension, 2D. What exactly it means? Okay, if we take a look at the this example, okay, if our kernel is 3 by 3, so we can draw a lot of different squares. Okay, a lot of different squares right here. And again, as we mentioned, those are X, right? and there will be 32 different kernels. They will go through the entire images and create another 28 by 28 hidden neurons. Okay, so that step means they are trying to find if there is a certain pattern. The pattern means the black color and the white color and gray colors. If there is a certain pattern exists in the entire images and where it is. So if some kernels, okay, for example, right here, it says, okay, that is exactly the pattern I would like to find. And this 3 by 3 kernel would output a very large number as we mentioned before. Okay, and after activation function, the number is still large, right? That means, okay, I find something which I would like to find right here. So that is convolution. Okay, so after convolution, let's take a look at this one. Okay, after convolution, okay, for example, we have H1 right here. So when I draw H1 right here, that means H1 is from X1, X2, X5, and X6, right? It is some kind of linear combination of X1, X2, X5, and X6, and then we have another activation function, so that is H1, right? H2 right here, that is 2, 3, 6, 7, so that's H3, and that's H4, H5, H6, H7, H8. Okay, something like 2, H20. So basically, those neurons are seeking some localized features, localized patterns in a small area. And in this example, it's 2 by 2. And in our handwriting number, the kernel size is 3 by 3. Okay, so after that, okay, think about one thing. If we have 32 different kernels, so after that, we will have 32 different kernels, and for each kernel, we have 20 hidden neurons in each kernel. So the size of the neurons at the first convolution layer will be very large, comparing to we have only 20 different features at the first place, right? So the information expand. Okay, so usually after convolution, we will add another layer, which is called pooling layer. They help us to organize the data again, to shrink the size of the neuron. So how do we do so? Okay, so take a look at this. We have 20 different neurons right here, right? H1 to H20. Okay, so the next step is, again, we select a pooling size. Okay, for example, it's 2 by 2. It is not necessary to use 2 by 2. It's the same as your kernel size, but in this example, it is 2 by 2. So that basically, again, you draw a square 2 by 2, and you can see that in this small area, we have H1, H2, H5, and H6. And for pooling, that means we need to organize these four value, H1, H2, H5, and H6. Okay, and for pooling, it also has stride. But stride right here, we set it to 2 and 2. That means every time when we move the pooling area, we move 2 Okay, so the data will not be overlapped if your pooling size is 2 by 2 and your stride is 2. So your data will not be overlapped. So next one will be this one, and next one will be this one. So if you use pooling size 2 by 2 and your stride is 2 and 2, that means you can divide the entire H1 to H20 to 4 different groups. And we need to calculate something to represent each pool. Okay, so for the pool 1, we have H1 and H2 and H5 and H6. And as we mentioned before, the number, the H1, H2, 5, and 6, if the number is larger, the value of H1, H2, H5, and H6, if they are larger, that means this neuron is activated. That means it matches certain kernel, right? So basically, to design the pooling layer, okay, we have pooling size, we have stride, and the next thing we need to decide is we need to select, so it's right here. So again, for pooling, right here, okay, basically we select the information from H1, H2, H5, and H6, right? But we select the biggest one as the P1 neuron. And for P2 neuron, okay, we have stride 2. So the next part will be, I think will be H3, H4, H7, and H8. And we select the biggest one. Because the biggest one represent here, there's a neuron, H1, 2, 5, 6, and one of them, okay, the biggest one is better match some kernel. So in this case, we can shrink the size of the neuron because when we select 4 out of 1 out of 4 to select the biggest one, so that we can have a smaller neuron size. Okay, so in this case, again, the pooling size is 2 by 2, and as you can see that the pooling size and the kernel size is different. Okay, so over these 4 different values, so we select the largest one, so let's call max pooling. And the stride none means non-overlapping. Okay, and padding same, that means sometimes when we do the pooling, okay, sometimes there are still some neurons cannot be divided by 2 by 2, for example, in this case. In this case, we can perfectly divide the H1, H2, H3, and H4 to H8 to 2 different groups, right? But sometimes the size of the hidden neuron cannot be divided by 2 by 2 pooling size. So sometimes you still need padding, okay? So the padding is the same. So in this case, we can shrink the size. We only select the biggest one out of 4 different hidden neurons in the previous layer. So that is, we call one set of convolution, including 1 convolution and 1 pooling. And after that, we still add additional 1 convolution layer and 1 pooling layer. So you can see that you can always find a very nice figure, right, from the internet. Is that something like that? Okay, in the previous in the first layer, that is the input layer. Okay, we have a 28 by 28 images, right? And we have the first convolution. The first one is padding is yes. The kernel is 3 by 3. Stride is 1 and 1. So we will create the kernel is 32. So that means we have 32 different weights. So there will be 1 weight, another weight, another weight, another weight, another weight, another weight. We have 32 different weights, and each weight will scan the entire X and create the output, which is still 28 by 28 because we padding the images, right? So that's called convolution. So after that, we have a pooling layer. The pooling size is 2 by 2. The stride is 2. That means overlapping. So 28, 28 will become 14, 14 because the kernel size is 2 by 2. Right? But we still have 32 different kernels. So we have 32 different outputs, hidden neurons. So that's one convolution. And we have another convolution right here. And again, we have another kernel, stride, padding. So the K now is 64. That means we use additional 64 weights on those max Boolean result. And we will produce 64 different kernels and outputs. And each one is 14 by 14 again because the padding is true. And after that, we need to organize the data again. So we use another max pooling layer. The pooling size is 2 by 2, so it's the size of 14 by 14 still shrinks to 7 by 7. So in the previous convolution layer, the idea is that can we find some kernel which focus on small area, which is 3 by 3. So I would like to find if there's a certain pixels matches to the kernel. And we have 32 different kernels. And it matches, then output it. Okay, if it does not matches, the number will be very small after activated function. Okay, so for the pooling, okay, we only select the biggest one out of the 2 by 2 kernel. That means we only because we only focus on the neurons, hidden neurons, which output a large value, right? So after that, we have the second convolution layer. That means I'd like to figure out if there's certain patterns in the second convolution layer. So we have 64 different kernels. Each one is 3 by 3. But as you know, the 3 by 3, because there is a pooling before the convolution. So although that is 3 by 3, but it somehow it means I would like to see if there is certain bigger structures among the pooling layer result. So for example, for the first kernel, okay, for the first layer kernel, there may be some small area like this, right? But after pooling, okay, for the second layer of structure, they may try to focus on, for example, okay, let's take some example. Okay, this one. For the first layer of convolution, okay, this kernel maybe they're trying to find some straight line, right? Straight line, right here. And for some kernel, some other kernel, they may be trying to identify a line, slash line, okay? And for the second convolution, okay, the point of view, okay, they may try to figure out, okay, if there is certain patterns, which is at the right top side, there are 2 slash line, and at the left top and bottom, there is a straight line. So the second convolution layer, they're trying to figure out some structures which is much bigger, okay? For the first convolution, they're trying to figure out is some localized small patterns. And for the second convolution, they're trying to figure out if there's certain much bigger structures or patterns, try to figure out. Okay, so after that, we have the information of the images. And after that, okay, you know, we still use the old structures, which is a dense neural network. So we have 64 different kernels, and each one is 7 by 7. So in total, we have 3,136 different neurons. We don't know how to handle it, so we simply just flatten the matrix to a single dimension, and we have 3,176 neurons, and we design a 2 different dense layer. Okay, the first one layer has 128 neurons, and the other one has 10 different neurons, and that is why, because we have 10 different classes. And of course, those neurons has activation function, and as I mentioned, for the output layer we apply softmax. So after that, we can this image, the information of this image will pass through the convolution layer to characterize the localized information and try to reorganize the information by pooling and trying to find the big structures by using another convolution and another pooling. And after that, all the information will be gathered right here in the flattened layer, and we use additional 2 dense layer to do the prediction. So that is. Okay, we stop right here. We'll talk about how to train the model next hour.